Welcome back, everyone, for section B of this paper, Unit 1, June 2024. This question is about silver. Silver chloride decomposes in light. This reaction was used in the first photographic plates. Write an equation for the decomposition. So, silver chloride decomposes to form silver solid along with chlorine gas. Now, you see, this reaction is actually a reversible reaction. If you look into that. But you don't have to write this one in your answer, actually. Let's just practice this. Okay. So what happens is when light is actually shown on silver chloride, it decomposes and it produces silver for which it gets shaded. And when again the light concentration is less, it goes back and it produces a silver chloride. As a result, the shade goes up. So you see the Polaroid glasses, they use this mechanism actually. Silver can form in displacement reactions, state two observation that is made when copper metal is added to silver nitrate. So you see when copper metal is added to silver metal, okay, the equation is written over here. Okay, so what happens is copper is going to react with the silver nitrate and blue color is going to be formed. This is due to formation of copper to nitrate, right? And the silver mirror appears is because of the silver. If you look into the equation, write the equation for this displacement reaction, includes state symbols. Copper solid reacted with silver nitrate produces silver along with copper to nitrate, right? Yeah. Okay, describe the bonding in pure silver metal. Include a 2D diagram to show 12. Okay, so 12 of those silver ions are shown over here. Positive array of, we can write down positive ions, array of positive ions. So we have seen, we drew 12 silver particles over here, and you make sure that the sea of electron and the array of positive ions are actually in the ratio of 1:1, right? So that, like, because one silver ion is going to lose one electron, which gives us the positive charge on silver. Now, since they are asking to describe, we need to write down that there is an electrostatic force of attraction between the positive metal ion and C of delocalized electron, right? Okay. Pure silver terms are too soft, so small amounts of copper are added to make an alloy. Explain why copper makes the silver less malleable. Malleable means that we can actually change the shape. And how do we change the shape? By sliding the layers when a force is applied, right? So what happens is copper ion is actually smaller than silver because obviously silver has a large number of shells. When copper is added, the smaller ion actually disrupts the regular layer. And what happens is the layers are no longer be able to slide over one another. As a result, they cannot be changed into shape. So they are no longer soft anymore, right? Now, the next question. This question is about silicon. Describe the relative atomic mass. It is the average weight mass of an atom compared to 1/12 the mass of carbon-12 isotope. So, isotope. Next, relative. Calculate the relative atomic mass. We need to calculate the relative atomic mass. This is how we do it. And if we actually look into the answer, if we plug in into this calculator, we will get a value of 28.2 actually. 28.2. Now we need to give it in the three significant figures. So that's why the answer is going to be significant figures. Make sure a lot of students actually forget about this three significant figure thing, and there is a marks for that. In the mass spectrum of silicon, there is also a small peak at m by z 14. Deduce the formula of this particle. You see, the main silicon is actually 28. Now, this value is half of that. And this thing is actually mass by charge. So if we just make the silicon's charge 2 plus, then 28 over 2 gives us 14. That's why we get a tick at m by z 14. Consider the elements Al, Si, P, and S. Explain the trend in the first ionization energy of aluminum, silicon, and phosphorus. Okay, so as we go from actually aluminium to silicon to phosphorus, the ionization energy will increase. And why is that? This is because the proton number, or you can say nuclear charge, right? The proton number increases. The proton number is actually increasing. Since the proton number is increasing, it will attract the electron more effectively, and as a result, more amount of energy is going to be required, right? Okay, this is one, and the other one is actually the electron is being removed from same shell, same subshell actually, same subshell. So for which the shielding effect just remains constant, right? The shielding effect does not change that much. So that's why it is the same, right? Why explain why sulfur does not follow this trend? Why it does not is because let's talk about from what happens from phosphorus to sulfur, let's say. So in phosphorus, the electronic configuration is actually 1s2, 2s2, 2p6, 3s2, and 3p3. The same thing is over here, except for 3p4. If we draw the 3p subshell over here, we see we have one electron, one electron, and one electron, 3 ones over here. And but for here, we will see that sulfur actually pairs an electron in 3p orbital. So you will write down this answer that sulfur has 4 electron in 3p subshell. So due to spin pairing, a slight repulsion occurs. For which sulfur does not follow the trend. Okay. All right. Next, carbon exists as several different structures called electrodes. Complete the dot and cross diagram by adding all the electrons in the outer shell of the 5 carbon atoms in the diamond. Okay, so in diamond, you see in diamond, carbon makes a bond with 4 other carbon atoms in a tetrahedral manner, right? So all of them will have bonded electrons. So dot cross cross cross. Okay, so let's write it bigger so that it makes sense. Let's talk about this one, right? So dot and cross, 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 right? This covers this. There is going to be another one over here, somewhere in the middle of this one here. Same thing. Like this, right? So you can think of it that there is going to be another atom of carbon here, then another atom of carbon here, and then some here, some goes here, and then one gets here, It's one with zero, right? That's how the interlocking structure is going to spread out throughout the structure of diamond. Draw a level 3D structure of graphite showing two layers, at least 13 carbons each. So we know that one carbon bonds with three other carbon atoms in graphite. So let's just sketch a simple structure of graphite like this now. So if we just add them up, it will look like this, right? It will look like this. And now this dot represents carbon. We can also give the symbol of carbon over here. If we repeat this, let's say we do it like this now, and then we have another carbon, 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 carbon. Yeah. And then the bond, one carbon bonding with three other carbon atoms in each layer. And this is the inter weak intermolecular force, you can say. Now we need to level this, right? So this is my weak intermolecular force of attraction. Okay, so that's why diamond has a greater density than graphite. So we know in diamond, all the carbon atoms are bonded strongly, very close to one another. But in graphite, so carbon atoms are in layers. And since there are space between the layers, that's why the density in graphite is less, right? The layers are far apart. That's why, graphite is less dense than diamond. Next question is baking powder is added to cake mixture to make cakes rise while releasing a gas during cooking. Baking powder contains an acidic derivative of tartaric acid and about 30% by mass of baking sodium and hydrogen carbonate. The baking powder releases the gas in two types of reaction during cooking, one of which is neutralization. Give the name of the second type of reaction. The second type of the reaction is going to be decomposition reaction. Decomposition. Decomposition reaction. Suggest why neutralization does not occur in an unopened container of baking powder. You see, for neutralization to happen, we need some kind of an acid, right? Now, since it is unopened, it is talking about the atmosphere. The only component that can act as an acid in the atmosphere is the water. Why? Because sodium hydrogen carbonate is actually slightly alkaline when dissolved in water. So you need to write down that water is needed for neutralization reaction. Neutralization reaction. Okay. The acid derivative of tartaric acid contains 20% potassium, 25.5% carbon, 2.66% hydrogen by mass, and the rest is oxygen. Calculate the empirical formula. Let's find out the oxygen first. So oxygen is going to be 100 minus 20.8 minus 35.5 minus 2.66. If you plug in the values in a calculator, you will get that the value is actually 51.04. Now to find the empirical formula, we write down potassium K, then carbon, then hydrogen, and oxygen. Potassium is 20.8, carbon is 25.5, this is 2.66, and this is 51.04. Now 20.8 divided by 39.1, it is the molar mass of calcium, potassium. 25.5 over 12, 2.66 over 1, and 51.04 over 16. These are all the molar mass of individual elements. Now we get the value of 0.532. Here we get the value of 2.13. This is 2.66. And this one is going to be 3.19. Now, the smallest one is 0.532. So if I divide all of the numbers, I mean 0.532, 0.532, we get a ratio of 1, 4, 5, and 6. So your empirical formula is going to be A Q4 H5O6. Okay. The acidic derivative of tartaric acid can be represented by the formula H plus K plus A 2 minus. Write an equation for the neutralization of sodium hydrogen carbonate by this. Okay. So H plus K plus A2 minus plus sodium hydrogen carbonate is NaHCO3. This will produce Na plus because this is going to lose the H plus. So K plus A2 minus plus H2 is going to come over here. So we are going to get H2O along with carbon dioxide, CO2. So this is the equation for the neutralization. Calculate the maximum volume in cm cube of carbon dioxide gas released by neutralization reaction in B2 from 5 gram of baking soda. Baking soda contains 13% baking soda by mass. Okay, so first of all, let's find the mass of baking soda. Mass 30 by 100 times 5 gram, which gives us, we do this here, 30 by 100 times 5 gives us 1.5. 1.5 gram. Okay, this is the mass of sodium hydrogen carbonate. All right, now let's find the moles of sodium hydrogen carbonate. Mole will be mass by molar mass. So mass is 1.5. Molar mass of sodium hydrogen carbonate is 23 plus 1 plus 12 plus 16 times 3, which gives us a value of 0.017. No, let's say this is the low. Okay. All right. Now we need to use the formula PV is equals to nRT. PV is equals to nRT. Now pressure is 101 0.000 times V is equals to N, we know, 0.0179 times R, which is 8.31 times temperature. Temperature needs to be in Kelvin, right? So 190 plus 273. Now, if I subject volume, this is going to be 0.0179, 8.31 times 463 over 101. Okay. The volume is 680. 680 cm3. Calculate the decrease in volume when the carbon dioxide gas is cooled to 20 degrees Celsius. So we will do the same calculation again, but this time the value of temperature is going to be different, right? So again, V will be equals to nRT by E. N is 0.0179 times 8.31 times temperature cooled to 20 degrees, right? So 20 plus 273 over 10100. Now the volume comes as 430. Now the decrease in volume is going to be, previously we had 480, sorry, 680. Now this is 430. So if we subtract, we get a value of 257. Next. Now question number 90. Both butter and margarine are fats used in cooking. Margarines are sold as unsaturated fats. State the meaning of the term unsaturated. Unsaturated means contains carbon-carbon double bond. Whenever there is carbon-carbon double bond, the compound is termed as unsaturated hydrocarbon, right? A degree of unsaturated can be determined by the reaction with boiling water, name the type of reaction. Whenever alkenes react with any other substances, they undergo addition reaction. This is going to be an addition reaction. Okay. The data plot a graph. For the simplicity, I have already drawn this graph over here. As you can see, the first part is going to be 1, 2, 3, 4. Okay. So 1, 2, 3, 4, and then the y-axis is going to be the volume, right? Okay. The data for the bromination of 0.5 gram sample of a margarine are shown. Calculate the mean volume of bromine water using all details in the table. Okay, the mean is going to be simple, 36.9 plus 34.1 plus 39.3 plus 42.5 over 4 values. We get a value of 35.7. Okay. Determine the average number of carbon-carbon double bonds per molecule of the unknown sample to two significant figures using a graph. Okay, so the value is 35.7. So if we go to 35.7, The answer is going to be somewhere over here, right? That's the value. And we can see that this value is about 1.25, right? So the answer in two significant figures is 1.25, so 1.3. 1.3 uh, carbon-carbon double bonds per molecule. Using the simplest alkene as an example, draw the mechanism to show the reaction with liquid bromine. Okay, so simplest alkene is just a ethane, ethene. So let's just draw ethene molecule here. And bromine is going to look like this, Br, Br. It will have a del positive this side and del negative here. The double bond is going to come over here and then on top. This one is going to come over here and then on top. Then we will get hydrogen, hydrogen. One of the bromine is going to be added up here. The carbocation forms here. And the Br minus is going to go in this carbocation. And we get our product. And the name of this product is going to be 1,2-dibromoethane. They did not ask for the name, so we're just not going to think about it. Okay. Name these compound by IUPAC naming system. Okay, so first of all, this is an alkene, right? So the alkene is prioritized first. So this alkene comes in the second carbon. So this is why 1, 2, 3, 4, 5, 6, 6 carbons. So the name is going to be 4-methyl. This is a hex 2 in 4-methyl hex 2 in. All right. Okay. Next, explain the meaning trans using a skeletal formula showing 4 carbons in your answer. Okay, trans means if they're talking about the cis trans, right? So for the 4 carbon atoms, if I draw the skeletal formula, one of them is going to be on the other side, the other one is going to be here. So we will write down trans means the priority group are on the opposite side of carbon carbon double bond. So they are on the opposite side of the carbon carbon double bond. One is over here and the other one over here. This brings us to our last question, which is 20. Many synthetic polymers are used in the home. Some are used as containers and others as coatings. PVC and PTFE are two such examples. Draw the discrete formula of the monomers. So chloroethane is simple, just one chlorine, and the other one are hydrogen like this. Tetrafluoroethane, on the other hand, is just chlorines. F, 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 S. Okay. Next, incineration and cycling are two methods of disposing of polymer waste. Give one advantage and one disadvantage here. So incineration have an advantage, which is that the energy is going to be released can be used to generate electricity. To generate electricity, right? And the disadvantage, it produces toxins. because it can contain multiple different elements which will be reacting with oxygen to produce toxic gases. Recycling advantage is it saves useful resources. Okay, useful resources are going to be saved, and the disadvantage is going to be it is very expensive. It's very tedious process to sort out the polymers and stuff which involves being it more expensive, right? So this concludes our paper for unit 1. I hope you guys understood the paper. If you did not understand any part, you can leave a comment down below. I will definitely reach out to you guys and try to sort your problems out. And if you want further more videos like this, please do subscribe to the channel, and that would mean a lot. And I am planning to produce more these papers as well as for IGCSE, AS, and as well as for A2. Okay, see you guys in another video.